Just a quick statement I want to make, and then you can start, Stuart.
All right.
Sure.
Yeah. So today's presentation is divided in two parts. One is about the DRTM specification, what it is, and to present that we have Stuart and Lucian, who are from ATG group, who has written this architecture, and from TFH side, the second part will cover the implementation details, and when we are going to when these all changes land in TFA master. So for that, me and Manish Badarkhe will be covering that part. So we'll start with the architecture features. Stuart will give a brief introduction to that. Okay. Over to you, Stuart. Thank you.
Thanks. Hi, everyone. I'm Stuart Yoder. I'm assistant architect in ATG and ARM. And so there's a new specification for DRTM, which stands for Dynamic Root of Trust for Measurement. And I wanted to just maybe spend about 10 minutes just giving you a brief overview of what DRTM is, kind of what problem it's trying to solve, and just a little bit about what the architecture looks like. So I guess next slide, Manish. So DRTM, Dynamic Root of Trust for Measurement, is a kind of boot security technology that uses TPMs to ensure the integrity of your target runtime. And so just to contrast dynamic root of trust for measurement with what we call static root of trust for measurement, it is the SRTM is where when you go through your boot flow, starting at say your boot ROM, every component that gets loaded and run is measured into the TPM. That means there's a hash of that component computed and stored in the TPM. That's one of the key capabilities that TPM has. And so this is a little different than your normal verified boot where you're using digital signatures. With measured boot, you record hashes, and then later, you can have a security policy around that. Next slide. Yeah, so the way it works is like an example of a security policy would be that you have a disk encryption key that's in the TPM. And unless those measurements of all the boot components were correct in the expected state, that encryption key will not be unsealed by the TPM, and you basically can't boot your OS because the disk encryption key is not available. So that's an example of a security policy based on the TPM and TPM measurements. Next slide. So one of the issues, and this is kind of getting to what DRTM is trying to solve, one of the issues is that the bigger your boot chain grows, the more kind of difficult it is to manage all these measurements and kind of rationalize that there wasn't a gap somewhere. And in particular with UEFI, it's arbitrarily extensible, and there are components being loaded and verified, say you have secure boot enabled, that come from option ROMs on PCI cards. You can have loadable EFI programs, and so the problem is that due to this arbitrarily extensible part of the boot flow, it's difficult to kind of rationalize and ensure that you have security. Next slide. So what DRTM tries to do, the goal of it is you get to a point where your OS runtime or hypervisor has been loaded by your bootloader. So you've gone through your normal boot flow and you've reached the point where you have your image ready to run, and we call that the payload here in DRTM. And so you then invoke a special launch command, and on x86, this is a special instruction. On ARM, this is an SMC call that notifies the DRTM implementation that there's a target payload ready to run. DRTM then measures that payload and puts the measurement in the TPM, and you effectively are starting a new chain of trust here. So even if the bootloader had been compromised by an attacker, maybe there was a bug in secure boot or something like that, when you start this new dynamic chain of trust, what DRTM can ensure that the new image you're running, that you get an accurate measurement of it, regardless of what came before, and then you can build a security policy around that measurement. And there's multiple measurements we'll talk about, but that's the gist of what DRTM is doing, is starting a new chain of trust with a fresh measurement of your target payload. Next slide. The thing you can also do is that you can repeatedly do this. So say that you have a running system, right? You have a system that's been running for 6 months, and you want to maybe upgrade your kernel or hypervisor. You can, without resetting the system, initiate a dynamic launch using DRTM, and you kind of basically are resetting the state of the TPM for the dynamic PCRs, and you get a fresh measurement of the new payload. And again, you can enforce a security policy, a TPM-based security policy based on that. Next slide. So basically what the security guarantee of DRTM is that when you launch your payload, that one, you're going to get a trustworthy measurement of that payload. So regardless of like any previous state in the system, DRTM is implemented in it's a trusted component, it's a root of trust. And so it will compute a hash of your target payload that it's guaranteeing is correct, and that is, not been, there's no issues with the integrity of that. And so in order to do that, one thing we have to guarantee is that there's no other agents in the system that could, write into this payload while it's being measured. So all cores are disabled except one boot core. So there's a single thread of execution. And so that means there's no other cores that can affect the payload. Interrupts are disabled. And so, no ISR can fire during DRTM and compromise the payload. There are DMA protections in place so that no DMA devices could access the payload. And then in addition to, that trustworthy measurement, using these mechanisms, we also provide some data to the payload so that it can actually start in a trusted state. For example, the memory map of the system is provided that's trustworthy. And so even if maybe firmware somehow had the memory map from UEFI tampered with, that could be detected using some of this data provided by DRTM. Okay, so this is a picture showing the ARM, just kind of the standard ARM privilege levels that people are familiar with. Next slide. The scope of DRTM is the non-secure world. So when we talk about reestablishing a new chain of trust using DRTM as the root of trust, we're talking about the non-secure side of the machine. So the secure side of the machine is trusted with respect to DRTM, and it's the non-secure side that we're effectively resetting. And so it really kind of looks like a warm reset of the non-secure side of the machine, where, again, this chain of trust is restarted. Next slide. So what this looks like on an ARM system is shown in this sequence diagram, where this is, I guess, an example. This is not necessarily how it would have to look as far as where components are located, but this is maybe a typical example, is that you have firmware at EL2. That's where UEFI would normally run. And so your bootloader and so on would be at EL2. At that point in the boot flow, you have a target payload that we call the DLME, the dynamically launched measured environment, loaded. And there's a new launch SMC call that is made that takes you into some EL3 firmware where DRTM is implemented. And you'll see that later as we talk about the TFA implementation of this, that's the kind of component we're talking about here. Is it's an EL3 component that handles the DRTM measurements, and then eventually transfers control to the DLME. So as you can see in this picture, a dynamic launch is really looks kind of almost like a branch to your payload. So you have your payload ready to run. You provide the address and some other information about that payload, and then DRTM takes various measurements and eventually transfers control to the payload, and then the payload continues. And then, as you can see with the arrows that go to the TPM, that DLME payload can then use the TPM. It can read the measurements out of the TPM to use them to base its security policy on. Next slide. The architecture also allows for what we call hardware-backed implementation of DRTM. And so the way this would work is there's a separate security coprocessor on the SoC that is where the root of trust resides. And so the architecture looks the same in both firmware-backed and hardware-backed, in that the client code running at EL2 does the same thing, but in this case, the launch SMC call results in the security coprocessor being notified to do a dynamic launch, and then there's potentially another firmware component we call the DCE involved here that would then transfer control over to the target payload, the DLME. So there are two implementations supported, firmware-backed and hardware-backed. And in the hardware-backed case, as you can see here, you basically have a smaller root of trust that is, in this smaller isolated coprocessor. Next slide. Just a couple more points about what you'll find in the architecture, and the spec is available now. It's publicly available on Arm Developer. Is that the preamble code that initiates the dynamic launch passes various parameters to the launch, including where the payload is, its size, the entry point offset, and so on. Also, it describes what memory is to be protected against DMA. And so there's a set of parameters we call the DRTM parameters that get passed during the launch. And the next slide. And then when the payload begins execution, there's a set of data provided to the payload. And that includes like what memory is protected, a trusted address map, the TPM event log for the DRTM measurements. There's a set of ACPI table information. I guess this slide is slightly out of date. I notice now that there's validated hashes of ACPI tables that are considered security critical. And so then when that target payload starts running, it can use this data to establish its new TCB. So that's the quick overview. The DRTM spec is available. I guess I don't have a link in these slides, but we can make that link available. And it provides a lot of overview material about DRTM, the threat model, what is in and out of scope with respect to security, and then the details of the architecture itself. And so, I guess maybe we'll pause here. I guess, Manish, do you want to pause here for questions, or do you want to keep going?
Maybe we can pause for questions on this section, then we can start with implementation.
Hi, yeah.
Stuart, Julian, go on.
Sorry. So yes, Stuart, will DRTM be used instead of UEFI secure boot, or as well as secure boot?
As well as, you certainly can do measured boot instead of verified boot, with digital signatures. But we envision, needing verified boot because it's just a defense in depth thing, right? If I think having both gives you, better protection, using digital signatures, does help verify that you're not, the integrity of what you're loading. But this provides a defense in depth thing to catch things, even if something slipped through verified boot, secure boot, could be caught. So I think that's what we'd recommend.
Yeah, and will there be any way, or would it be desirable to be able to exploit the hash that DRTM calculates for the secure boot decision?
I'm sorry, say that again now.
Will it be possible or desirable to be able to exploit the hash that DRTM will calculate for the secure boot verification step?
Yeah, I think it's going to really be orthogonal to that. So, with secure boot, you're verifying signed images using digital signatures, and so.
But I believe there'll be a common hash over the payload, which is quite a
well, like in a DRTM flow like that. Yeah, I think possibly when that payload was loaded by the bootloader, if it was signed, I guess yes, that hash would be the same. But I think I'm not sure it's necessary to really kind of intertwine those in any way. I mean, I think with DRTM, you have that trustworthy hash. And then again, the only way it has any effect is if you build some kind of TPM policy around it. And so, yeah, I guess I'm not sure, just thinking about it, whether or not the digital signature checking really, would play into that.
I suspect it would be a boot time argument for trying to exploit just the single pass over the payloads, and then to use that for the signature verification and for the boot measurement. Anyway, yeah, okay, yeah, it's overcomplicated things. Yeah, at the moment you're viewing them as being entirely independent.
Yeah, that's right. Currently.
Okay. Yeah, thanks.
They usually should be, right? Attestation is usually detection. Secure boot, you can think of it as prevention, right? And the prevention, detection, recovery. It can get intertwined, but in general, they should be, or at least in my view, it should be viewed as entirely separate, and they should be able to be implemented entirely independently.
Back slide, please.
Any other questions for anybody?
You mentioned there are two implementations. It can be either firmware backed or hardware backed. And I think in the firmware backed, I guess it's possible to have or instead of having all of the implementation at EL3, it is also perfectly valid to have most of the implementation lying at a lower secure exception level, like secure EL0, EL1 as a secure partition, and have only the enabling code at EL3. That would also be a valid implementation, right?
That is, yes. Yeah, the example I gave was just really an example. And so the architecture does not dictate where all the DRTM components live. And so, yes, that would be desirable, is to push as much out of EL3 as possible. And so that is valid.
Okay.
As you'll see, like in the following slides from Manish, is that we did do a proof of concept implementation in TFA that is forming the basis of what's going to be upstreamed. And there, just to keep it simple, we did not split it out of EL3 like that. But that would be desirable over the long term.
Okay, thank you.
So are we following any TCG like specs for event log kind of thing, or it's open?
Yes, we follow the TCG standard for the event log.
Okay.
I mean, there are some unique event types that are defined in the DRTM spec for ARM. In fact, there's a event number namespace that's been allocated to ARM from TCG that we use. But so we do have some unique ARM events that are logged, but the format of the log is following the TCG standard.
Okay, thanks.
Hey, Stuart. So just to expand on Sobi's question, the spec specifically says in a lot of diagrams and places here, talks about the specific exception modes. But you said one can relax that and run something in the secure EL0. So do you anticipate some changes in the spec to say that specifically, or say that you can relax this? It's just an example that we're talking about.
Well, I think okay, so I think we should maybe distinguish a few different things there. I mean, one is I think what we do say in the spec as far as exception levels go. I mean, Manish, maybe you could flip back to like the firmware backed slide, like the next one, the next slide. So, so we say that the launch must occur from the highest non-secure exception level. So if you had a system without EL2, you could do the launch from EL1. Okay, so that's like, one thing mentioned in the spec. As far as where the DRTM implementation is, in this picture, you can see it's at EL3. But an SMC call always takes you to EL3. But at that point, you do have the flexibility of implementing other parts of the implementation at other privilege levels. For example, you might have like the TPM. The TPM itself might be based on a service running at SEL0. And so maybe whether it's at EL3 or whether parts of DRTM are at EL2, they may make requests of the TPM that are running at SEL0. So I think what we don't say exactly, we don't specify how that has to be constructed with respect to exception levels, but I think the key thing is that when the launch occurs, you go to EL3, which is your root of trust, or on a hardware back case, it's the coprocessor, and then the initial measurement of that goes into the highest locality PCR and TPM, needs to be done at in that root of trust, and then from that point forward, you have flexibility in where the DRTM components, may live. I mean, I guess as you read the spec, if you find something you think really doesn't line up with what I said there, or that, would suggest you have to be at certain privilege levels, let me know. I mean, I think the intent was to show examples in the spec and not to have, that's not normative that, which exception levels everything necessarily reside at.
Right. Okay. Thanks. Another question about the DMA and memory protection that the spec talks about. I know you have not gone through it in the slides, but there is a specific statement which says that all the DMA capable agents should be behind an SMMU. So
right.
Just a generic question. I'm not saying that this is specific to any platform, but does that mean the spec will not support any platforms that do not adhere to those requirements, or they allow the platform to implement that requirement in whatever way they feel is possible?
Well, the one thing that the spec distinguishes is what we call non-host platforms and devices. And so, so for example, if you have say a controller on your SoC, like maybe it's like the SCP or something like that, that's a trusted component, or the SMMU itself or the GIC do memory accesses and they're trusted. And so if you have a component, a hardware component that does DMA, and you consider it part of your trusted computing base, that it is absolutely trusted, then that's okay. So we call those non-host platforms. But if you have a device like, say, a PCI NIC card that then and it's not behind an SMMU, then that wouldn't comply with the system requirements, because you're opening up a risk to DMA attacks from devices that are not behind SMMUs. And so we do try to make a distinction there, that whether a device is part of the TCB or and is considered a non-host platform versus a peripheral device that really should be. And so I think we currently don't have a compliance program against the DRTM. And so if you have wide open DMA into your DLME, payload, then, it's definitely a security risk, and that we're trying to prevent. And so I think it would, certainly go against the spirit of what DRTM is trying to do, which is to guarantee that nothing can tamper with that DLME while it's being measured and while it's running.
So, Stuart, I guess the other aspect of it is that if a partner is not using an SMMU for DMA protection, does that, and they're using their own IP to achieve the same effect, does that fall foul of the DRTM spec?
I guess,
if I can jump in for a second.
Yeah, go ahead.
The reason why you need the DMA protection to be available even outside of the DRTM environment is because the operating system that is launched by DRTM needs to be able to protect itself from DMA attacks. So if you have a proprietary mechanism that is not visible to the operating system, but is just being used to service the DRTM launch, that would not be sufficient.
I think the other thing that the spec allows, it does allow, what we call like a page granular, region-based memory protection, whereas you can have a proprietary mechanism that protects the DLME, so that would allow you to even do DMA perhaps while DRTM is in progress. So we do allow an alternate mechanism, and so we call that region-based memory protection. And so that, I guess if you take a look at the spec, what's described about region-based protection is that there is an alternate mechanism allowed to protect the DLME, but without an SMU, yeah, I think you have bigger problems like, with your OS itself. So I guess the region-based protection doesn't mean you don't need an SMMU. It just means that for DRTM specifically, you can use that mechanism to protect the DLME instead of an SMMU.
All right, thanks. Yeah, where I was coming from is that it depends upon the market segment, right? Like SMMUs are prevalent in some market segments and they aren't in others. So, yeah, whether we can still support DRTM or not. But yeah, thanks.
Okay, so I think we can now move on to implementation part, and then if time permits, we can go through further questions at the end. So on TFA, current status is we have got a proof of concept code, and we have created a branch. You can just access the code here on topics Arm DRTM proof of concept. This POC was based on 2.5 release, so quite old, and but it's if you are interested, you can have a look into the code and just play with it. But the disclaimer here is you should not be using it for products, real products. This is just for understanding the spec and the code base, and whatever the code for consumption in a product should be done from the master branch. The initial upstream support is planned around mid of this year, towards somewhere in June, end of June. And this will be tagged as experimental because there are quite a few features which are not yet fully implemented. Also, we are not sure about the full software stack. So like in any other new specification or new features, we keep it experimental for some time until it gets matured. The support will be initially on FVP platform, even though the proof of concept has a QEMU platform porting, but support of QEMU in open mainline is all depend on the people who are maintaining QEMU in trusted form array, and how many people are interested in getting this DRTM feature on QEMU. So if people are interested, we can we can also push the patches from TFA side for reviews, and it can get merged. So as Stuart said earlier, the current implementation, the initial phase implementation in TFA will be firmware-based implementation, and all the DC RTM and DC component, both of them are currently being part of EL3. But what we will do is we will guard DC against build macro, so that in future when there is capability not in in other parts of software, we can decouple it from EL3, which solves our problem of having a minimal EL3 code. So in DC, the DRTM preamble, this requires some preconditions to start the launch, and one of those are like single PE execution. So EL3 code will make sure that the preconditions are met by making sure that single PE is executing before the launch. Also, the non-secure interrupts are disabled. There will be change in SME v3 driver, which is generic code in EL3, to abort all the non-secure pending transactions, and also disabling SMME before launching the DLME. And this is currently only complete DMA protection. There is no region-based protection yet. Yeah, so the next is all the DRTM standard services. They are implemented. Some of them are implemented. There is a slide about SMC calls in next in couple of slides. The DRTM implementation will coexist with the current TFA trusted boot, and we have support for DR. So the parameters which Stuart told earlier, that which is passed from DC preamble to the DRTM implementation. So there will be parameter parsing support in EL3 code base. Also, there will be crypto support for hash calculation of various DRTM components, and on event log driver, there will be support to record the hash measurements of various DRTM components, and also to attach it to DLME data. So DLME data is what we pass from DRTM implementation to the payload. And there would be platform hooks which can be overridden by platforms to retrieve the address map and attach it to DLME data. Also to retrieve the base addresses and number of SMMU to engage DMA protection. And finally, there will be a platform hook to read and write DRTM errors to non-volatile memory. We'll see about the DRTM errors in next slide. And finally, there will be a CI configuration which will be running nightly on TFA CI, which will use a pre-built DRTM application which contains both DC preamble and the payload. So on SMC call support.
Hey, sorry, quick question.
Yeah, go ahead.
Is the DLME data built into tables or something into the image?
So this will be,
does that come from non-secure?
No, it comes from DC preamble. Yeah, go ahead, Stuart.
Yeah, the DLME data is provided in memory by the DRTM implementation. And so actually the next slide after that. So the memory for the DLME data is allocated by the preamble, but it's populated by DRTM. So the data in this data structure, is kind of trustworthy because it comes from DRTM. And so no, it's not built into the image. It's just in memory, and it's populated by the DRTM implementation.
Okay, thanks.
So the number of SMC calls which is specified in the specification are one is DRTM version, which is currently fully supported. It will be part of the first release. There is also the features, DRTM features, which determines the supported DRTM capabilities. That too will be fully supported. The DRTM dynamic launch is the SMC command, which actually starts the launch of DRTM. So this is currently partially supported, but it works it works with the current proof of concept. The limitations which we have, and that's why we call it as partial support, because we are measuring the image and data components, but not all of them. So whatever has been mentioned in the spec, not all the image and data are currently measured. That's why the partial support. We are doing a complete DMA protection, not region-based protection, and also the DLME data which we are preparing. It does not contains all the data which is mentioned in the specification. That's why this SMC call is partially supported. On DRTM on protect memory, this removes the memory protection put in place by the dynamic launch. This is also partially supported now. On closing locality, this is not supported because there is no physical TPM in current POC, so this won't be there. And on DRTM get and set error, this is implemented in a sense like we'll provide platform hooks to write to non-volatile memory and also get those error after. If the DRTM has failed, then the errors will be saved in some non-volatile memory, and then next time when you boot the system, it will get the error and do the remedies based on error code. So these two are fully supported. On setting and locking TCP hash, this is not supported because these calls are not yet being made by. So these calls are supposed to be made even before DC preamble to load. For example, you calculate ACPI table hash and then you save those hashes and lock it. So this call even goes before DC preamble, and currently there is no such call made from the UFI side. So these two SMC calls are currently not supported. Any question on this? So finally, the limitation of the current, the first delivery in June is this is only targeted for 2-world systems. So people who are familiar with the new ARM CCA, where 4 world are there. So we are not still going there. We will show our implementation only on 2-world system. The assumptions are there is no secure payload running which can impact DRTM. So that has to be guaranteed when DRTM is launched or running. And also there is no request to power on secondary core. So one of the pre-requirements are to run the system on single P. So we don't expect any P to run during the whole DRTM process. As we said earlier, there is complete DMA protection in the current implementation. There is no region-based protection. The event log driver, which is currently different for measured boot and DRTM, ideally there should be a single driver, but the current implementation has both SRTM and DRTM has their own event log driver. But at some point we will merge those driver in a one single driver. And on the SDI, disabling SDI events, there was some discussion ongoing, but the conclusion is DC preamble should make calls to disable all the SDI events by using few of the SMC call already present in SDI. So these calls are not yet made, but what we can do from EL3 is we can make sure that before doing the dynamic launch, these all events are disabled. So these are the current limitations which and we will try to fix these limitations after the first phase of delivery. So that's pretty much it from the implementation side. Is there any questions?
Hey Manish, on the last slide, I just wanted to understand this, the assumption where you say no requests to power on secondary cores. So is it, because the spec already says that, so I'm a little bit confused why you're saying that that's an assumption.
So if I think from the EL3 point of view, we won't stop any call for powering on a secondary core during that phase, right? So it's a responsibility of the DC preamble or whoever has launched the non-secure side, which has launched the DRTM, should not be forwarding such SMC calls to power on secondaries. So this point basically is from EL3 point of view.
Oh, I see. Okay, so the assumption is that so EL3 will not specifically go and check the secondary cores are on or not.
No, it will check before the launch.
Yeah.
Yes, that all the cores are off, but during the DRTM process, it can't stop any call coming from non-secure vault to.
Okay.
Yeah.
Okay.
I guess in theory, since there are no other cores running, you're only on the boot core, there shouldn't be any way for that to happen anyway. I mean, it certainly is a true assumption, but in theory, I don't see how it could happen, but yeah.
Another question for the platform hooks. Are there plans to also introduce region-based DMA hooks? Or that won't happen for the first delivery?
That certainly won't happen for the first delivery.
Okay.
Yeah.
So
I guess the one challenge with that is that, region-based protection, assumes like proprietary hardware that, has special region-based, memory protections, that supplement the SMMU. And so, the FVP or QMU, don't have such a thing. And so I think, so I think the one limitation there is just having a platform that actually has the mechanisms to do it. So yeah. I guess one other thing I'll just add real quick is that, one limitation, is that there's not a client provided, that uses DRTM here, right? This is just the TFA side. And so, and so in order to actually try it out or use it, at this point, you would need to create your own client. We have a simple crude client we were using for proof of concept work that I guess not ready to be shared. And so, I mean, the hope I have, at least from the DRTM architecture point of view, is to eventually provide a client that can verify compliance with the architecture. And so, if you implement DRTM, whether it's in TFA or however it's implemented, that we can provide a tool that can run, maybe from like an EFI program like that can verify whether that implementation complies with the architecture. And so, so that's, not, I don't have a roadmap for that yet, but that is a goal to provide.
So I assume that the DL event should always be executed on the core 0 or the BSS, and hypervisor should be core aware, right?
Your question is whether it should always be on core 0?
Yeah, right. I mean, it should be executed on core 0, right?
I think it should not be mandated, right? It should be the last core.
I think, I don't know if Brian can help me out here remembering what we said in the spec, but I think what we said is that.
Oh, sorry,
yes?
Go ahead.
I was just going to say that
there's a feature request. You can ask it the core ID of the one that is supposed to run DRTM.
That's right. Yes, we advertise in features which core should be used. Yeah, that's right.
Yeah, so it is like affinity in the MPIDR we are providing back to the client, like on which boot P we want the DRTM to work.
Okay, so it's not, okay, yeah, that's what the country, so it is not mandatory that it should be on the bootstrap core. It can be any core and all other cores need to be shut down. Okay.
Yeah.
Well, but just to be clear, there is a core, a specific core that is advertised in the DRTM features that where DRTM needs to happen, but it doesn't have to be core 0. But you do need to follow what that advertised core ID is. Yeah.
I mean, basically DRTM can be launched at any point in runtime of the system. So there is no concept of boot P at that point, right?
Right. So now I'm curious, I mean, how this would happen with multi-socket cores this time, if it is launched on non-BSS.
Yeah, we do mention multi-socket in our system requirements, and I guess the current view is that a multi-socket SoC, would simply look like, from a software point of view, just like an SMP system. And so somewhere there's a boot core, and we would expect DRTM to happen on that core. And so whether how the other sockets cores get started and stuff is kind of out of the scope of DRTM, but we require that all PEs be shut down except the boot PE, whichever socket that is. And then, so yeah, if there was a model where, say, you have 2 sockets and both sockets somehow boot simultaneously or something in parallel, we haven't really encompassed a model like that for DRTM, and we're assuming that it's just a single boot core.
Right, because secondary socket may not have the DPM connected to it, and then it complicates things a little.
Yeah.
Well, actually, I mean, along those lines, right? So that can be a problem in your hardware-backed model, right? So typically, if you've got multi-socket systems with each of the sockets having 2 different SCP equivalents, and if that is the a root of trust for measurement in that case, it would be interesting to figure out how to coordinate between those SCPs.
So yeah. So if I understand correct, Stuart, so is still open for the discussion for multi-socket use cases. Is that what?
I'm sorry, say that again. What was the question?
So is the spec still open to include the multi-socket cases? I mean, it's still worked on. Is that right?
We at this point, if you look at the system requirements section, we have a brief statement about multi-socket, but I think that it's a beta spec. If there are, if there's something about multi-socket, that we're not encompassing, or there's some, some detail there, yeah, we're happy to try to address that. But we did attempt, at least for the firmware back case, try to address the question of multi-socket. Yeah, one other comment is that the hardware-backed implementation or definition in the spec is currently at alpha quality, because there were some questions about it that we did not have time to sufficiently, prototype or prove out. So that's why it's at alpha. And so that is one of the current open architecture tasks, is to address hardware-backed, in further detail. Yeah, I guess a multi-socket sounds like probably one thing should be on that list of how does hardware-backed work in a multi-socket system. But yeah, the spec, I mean, it's a beta spec. We can make changes if there are areas we need to.
Okay, sounds good.
Manish, can we go to slide 10? I just wanted to clarify something if people weren't aware. So, what we're trying to do with the TFA team, which is both Manish's who are doing the implementation, is doing that DRTM implementation, that's that green box in the middle there. And we'll be working to introduce into the TFA project appropriate tests and CI to test all the interfaces in and out of that implementation. And another big reason why it's initially going to be marked as experimental is the other pieces that need to be there for the solution need to be provided by partners and other projects to enable the usage of that. So you could think of what we're doing is the DRTM, this whole solution enablement by providing that aspect. Hopefully that's come across in the presentation and everything that the folks have done, but I just wanted to make that clear if people were thinking the TFA project was providing implementations of all aspects of the solution. And hopefully this tech forum is a way of getting community and partner engagement on helping us produce that enablement, and hopefully they the other bodies and other pieces can make use of that.
One other thing to mention that I think Manish touched on this, but just to mention also is that the two platforms we we did the proof of concept work with and that we're starting with on the implementation don't have TPMs, right? So the proof of concept, we didn't need a TPM to prove out the interfaces, right? We were able to basically, for the kind of back end of the TPM, we have like kind of a simple data structure and memory where we can kind of simulate PCRs, if you will, that as we make measurements. And so that's one thing missing is that is an actual TPM implementation here. And so, but I think again, it's obviously need that for production, but for purposes of proving this out wasn't top of the priority list.
So out of curiosity, is there a long-term plan for evolving the POC branch into something product quality, or is the expectation that we do a POC to prove the architecture and ARM is done with that?
Well, just to clarify, so there's a POC branch, as you can see here, that's there, and that's not really going to evolve much. That's kind of what we did as POC work to kind of prove out the architecture. What Manish and his team are doing is based on that, they're actually upstreaming into the master branch of the DRTM implementation. And so yes, we are, for the core part of DRTM, that is what's being upstreamed in TFA, with like mid-year, with the goal of mid-year having something. But that still doesn't include like the end-to-end flow, like with a TPM and so on. And so, I don't have anything to say about as far as kind of an end-to-end reference flow that includes everything, including the platform pieces, TPM. I mean, that's kind of a follow-on to this base core enablement that they're doing.
Okay. Yeah.
So whatever.
Okay, it'll be interesting to. Sorry, go ahead.
Sorry. Yeah, just to clarify on that, whatever goes in TFA master will be sort of production quality. But the only thing is it's kind of EL3 is enabling things, but for having an end-to-end solution, we need a lot of different pieces. So EL3 part is one of those pieces, and if it goes in master, it will be ready to be used.
Okay. Yeah. I mean, I'm just curious if things are going into TFA master, then it would be good to have some more discussions around whether we should enable it in EL3 or start off with pushing things to lower exception level.
Yes. That's
right.
Very interesting discussion which we need to follow up later.
Yeah. Thanks.
On the software strategy, one question, Manish. There are other components in this DRTM stack that reside in EL2, for example. And I understand you will only upstream the EL3 part. But then, what is ARM's strategy or plan for the other components that are outside of EL3? Is it just going to be upstream to TFA EL3 and then that's it? Or what do you envision?
So, I mean, this is one of the steps to make people more aware of this DRTM spec, right? And we want more sort of engagement from different partners. Maybe Stuart can answer that, but I expect that people, once they start to get interesting, they will do the other parts of it. Definitely.
Yeah, the one there is an open source project called Trench Boot, which is includes components from Grub, which does the dynamic launch, and then launches like a Linux-based DRTM solution. And so so we certainly want to support Trench Boot. I mean, I think at this point, ARM doesn't have a specific plan around Trench Boot support, but I think, I mean, Windows is another piece of this. And so we work with Microsoft in the architecture, and we verified the basic architecture using a Windows boot flow. So there is that's kind of a POC level Windows validation of this has already been done. But as far as kind of open source DRTM, I think Trench Boot is seems like the most likely open source project that could use this. But at this point, there's not a specific plan for Trench Boot enablement. And again, I did mention, like, we do hope to provide a test client as well that could use to validate the architecture or kind of have verify compliance, but that's kind of also further out in time.
Right. I think in the past, ARM has inclined towards TFA tests to include some of the other software components. So is that on the table? Are you thinking about on those lines?
So on TFA test, we will initially verify definitely the SMC calls, make sure that they do follow what SMC what is mentioned in the specification. The other thing is with the help of TFA test, we will test it in our CI with the pre-built application, UFI application, which is behaving as a DC preamble and the launch, the DLME data. So this is here I mentioned already. But yeah, the CI configuration with pre-built DRTM application. So this will be part of our CI, and that's the level of verification we will do from TFA for now.
So Manish, I mean, in our generic measured boot implementation, we've got the the FTPM test component. It's not a supported FTPM as such, but it has the appropriate APIs and ABIs that allow us to do a degree of testing against. I think the plan is to reuse that to some extent with this. Is that the plan?
Not yet, Joanna. We haven't planned about FTPM for now,
right? At
least for DRTM.
Yeah, and that's where it can start to get interesting in terms of pushing some of this to lower exception level, right? If you implement all of this in EL3 and you end up having an FTPM and secure EL0, for example, or even the TPM driver in secure EL0, it can start to get interesting.
Yeah, we will definitely start having more discussions around that, moving stuff from EL3 to other lower ELs.
Yeah.
And also, just to highlight what Trench Boot Stuart was talking about, what I can do is I will put all the interesting links where people have tried it in this slides. I think we are out of time now, and I hope we have answered most of the questions. If there is anything else, just send us an email to me or Stuart or on the mailing list. Yeah. Thank you. Over to you, Joanna.
Okay, yes, we're out of time. I'm going to stop the recording and I'll try and make these available on the trustedfirmware.org webpage in the next few days. Thank you for everybody's time.
Thank you.
All right, thanks all.